CircuitPython is more than a linear path. It's a programming language with endless possibilities. I am not the watcher. I'm Prof. G. And this is the CircuitPython School lesson where we learn to harness the potential of conditional outcomes where we ask, what if? And we learn to work with a digital I/O library, set up buttons, respond to button presses, and we'll work with conditionals and compound conditionals using if, elif, else, and or statements. So code superhero, let's learn big. Apologies for the dorky intro, I just watched Marvel's What If, but conditional logic, sometimes known as Boolean logic, will significantly enhance your coding superpowers. Now we did a lot of work in our last lesson, but in the next few lessons we're not going to be working with an LED strip, so I'm going to cut the power to my CPB by unplugging my USB cable, and then I'm going to unplug the 3 wires that were attached to the CPB. There's no harm in leaving the LED strip attached, but since we're not going to be using it in the next few code examples, I figured I'd unplug it. Now I'm going to plug my USB cable back in again, and even though the LED strip isn't attached, my code won't crash, it just can't light up any LEDs that aren't there. The animations that were previously coded for the built-in lights, though, continue to execute. Now we did a lot of work in the last lesson, and there's a lot of good code in here that we can raid and copy and paste whenever we want to repeat any of these animations. So it's a good idea to save this code in the CircuitPython school folder that we created in an earlier lesson. First, I'll make sure that the comment up here says lesson 8 Adafruit _LED _ animation, so I remind myself what this code is. Then I'll double click on the tab to bring up the Save As dialog in Mu. My CircuitPython school folder happens to be in my desktop. You should navigate wherever yours is, and I'll enter that folder, and I'm going to save it here as lesson 8 Adafruit LED animations. I actually saved a version of this file here earlier, but I'm just going to replace what was there. And now, very important, I'm going to double click on the tab again to bring up Save As one more time, and I'm going to navigate back to my CircuitPy volume and save the code here as code.py, and this makes sure that any code that I modify and save will be saved as code.py, and it's going to execute on my CPB. Now let's strip out the code that we don't need for the next few lessons. We can highlight and delete all of the from import statements for the animations that we used in the previous lesson because we won't be working with these for a while. Now there's no harm in leaving this in your code, but it does take up a little bit of space. It's really not too much, and we're not writing programs that are so big that that's going to make a difference. But I don't like to have unused code cluttering up programs when we're trying to illustrate new concepts. Now we can also scroll down and highlight everything from the code where we begin to define our strip and until just before while true, and then we can delete all of this code. So do keep in the 3 lines to define pixels. Remember, those are the 10 lights that are built into the CPB. We are going to use those, and I'm also going to delete everything else that's inside of the while true loop, but I'm going to put a pass statement in here, indented after while true, so that when I save my work, I'll make sure that I don't generate an error. Then I'll open the serial console. Now I'm going to press save. The code running in the previous animation is no longer there, so that animation stops, but I don't have any errors, and we've got a cleaned up bit of code, so we're ready to work on our new concept, which is recognizing when there's a press to either the built-in button A or button B on our circuit playground. And if you look closely at your CPB, you'll see that there are 2 push buttons that are labeled button A and button B. Now the first thing we need to do if we want to detect a button press on one of the built-in buttons in our circuit playground is we need to import a library. And this library is called digital I/O, all one word, all lowercase. And we do this in the way that we imported the NeoPixel library to work with our LED lights, or the time library where we worked with the time library function named sleep. Well, in the way that NeoPixel has commands to set up and work with our NeoPixel lights, Digital I/O has commands to work with any input or output that we use in our project. Now the next thing we need to do is we need to set up our button, which is an input device. Now remember, we had to set up our NeoPixel lights before we could work with them. We used the NeoPixel class in the NeoPixel library to create an object. We gave it a name, pixels or strip. Then we passed in a bunch of parameters. Well, we have a similar command in the Digital I/O library. It's called .digitalinOut. It's upper camel case, where we're working with a class here. It's like a blueprint for setting up a data structure. So this is going to create an object. And in this case, it's something that can perform either a digital input or an output. Now our button is going to be an input. We're going to be able to detect whether or not it was pressed. So inside the parentheses, when we call the class to set up this object, we say where this I/O device is located. And to access the built-in button A, which is on our circuit playground, we refer to this as board.button_A. That's all in capital letters, all caps snake case. The statement board button_A knows where button A is in the circuit playground, just like board.neopixel, all in caps, knows exactly where the 10 built-in NeoPixel lights are. Now to the left of the equal sign, this is where we give the button a name. We could give it any valid name, but button_A is a good name for button A. Now we're going to need one more line to set up this button. And that's this line here. Now what this line does is it says, hey, the object that we just created called button underscore A, we said this is some kind of digital input or output. So switch underscore to underscore input says we'll be waiting for input. So this button A that we just defined, it's all about the input. Then inside the parentheses, this is going to seem a bit obscure because we haven't done anything with breadboards or wiring circuits yet. So you don't have to know the specifics at this point. Just know that when you work with either the built-in button A or button B in a circuit playground, you need to set pull equals digital IO dot pull dot down, just as I've written it here with this exact same capitalization and punctuation. And again, we're going to cover this in a future lecture, but it'd be more challenging to try to explain this right now because we haven't done any real circuit design. So talking about current and resistors isn't going to make a lot of sense. Just to give you a taste of where we're going to go with this, the kind of circuit that's created by the built-in button won't give us a reliable signal unless we say pull down in here. If we don't do that, we won't be able to reliably tell if it's being pressed or not. Now, once we do that, we say, hey, if the button isn't being pressed, then we're going to report false for the button's value. We'll see how we program this in just a bit. But when it is being pressed, we'll report that, hey, the value is true. True means it's pressed. Now, describing pull down is harder at this point, so it's probably best just to remember that when you want to work with the Circuit Playground's built-in buttons, you need to add switch to input with pull equals digital IO dot pull dot down inside the parens with its exact same spelling and exact same capitalization and punctuation. Consider this like a reusable software Lego that you can copy and paste whenever you need it, and we'll cover more about pull down and pull up resistors in a future lecture where it's more appropriate when we're talking about circuits. So now that the button is set up, we can write code to detect if it's pushed. We'll check for that press down and while true, and we'll say if button underscore A dot value colon. Now the value property of button A will report either true or false, only those two values. Now we call values that are either true or false Boolean values or bools. They're named after 19th century mathematician George Boole. Cool to have a data type named after you, George B. Bummer you died in 1864 and never got to code in Python. Now anything indented after the if line is executed if the value in the if statement is true. When is button underscore dot value true? When the button is pressed. And if that button is pressed, we're going to turn all the lights on our CPB red, so we'll say pixels dot fill and in parentheses all caps red. Now what happens if button A underscore value is not true? That would mean the button is not being pressed. Well, we'll skip over any indented lines after the if statement. We won't execute those, and we'll continue executing the code after the indented line. So let's try out this code. First, I'm going to update my line 1 comment so that it says lesson 9, what if pushing buttons for this lesson. Then I'm going to import digital IO. I could define the button anywhere before while true, but I'm going to do it right after I define my pixels. And I'm going to create an object called button underscore A. I'll set that equal to digital IO. That's the library where I can find the dot digital in out class. And you'll notice code completion will suggest these values, so feel free to highlight the appropriate value, then type either return or tab. And when you type an open paren, we even get a little yellow help descriptor up top that says digital in out accepts a pin value, and this creates a digital in out object associated with the pin. What's the pin? Well, we didn't attach that button to a pin or a pad. It's just built into the board. But if we say simply board.button underscore A, and board is lowercase, but button underscore A is all caps snake case, this value knows exactly where button A is on our circuit playground. Then we set button A up as a digital input on the next line, so we say button A dot switch underscore to underscore input, and in parentheses, we write pull in lowercase letters equals digital IO dot capital P pull dot down all in caps, just like this. And code completion recognizes each value so you can see it pop up and just either tab or press return on the selected value. Then down in while true, we want to detect our button press, so let's delete pass, and over that we'll type if button underscore A dot value colon. Now remember that dot value property of button A is going to be either true or false. It'll be true if the button's pressed, false if it's not. If we press return after the if, the line is indented. Any lines indented just below if will be executed if value's true, so we'll say pixels dot fill and in parentheses all caps red. Now just to see what's going on, I'm going to use a print statement. I'm going to put a print statement just before the if statement. I'll say print and then in parentheses button underscore A dot value. That should print either true or false. Now here's the thing, the CPB executes so fast that if I don't put in a sleep statement to slow things down, print statements that show will be way behind the current button press. So in order to be able to see what's happening in kind of real time, what I'm going to do is I'm going to slow down the execution of my code. I'm going to put a time sleep statement in right after the if block so that the sleep will execute regardless of whether button A is pressed or not, making sure it's not indented so you can see it's at the same level as the if statement and the print statement. Time.sleep in parentheses 0.5, so I'll wait half a second. Then let's open up the serial console to make sure that we don't have any errors. We'll click on save. And we'll initially see a bunch of false values, and the CPB is not lit up because I'm not pressing button A yet. But when we press button A, the CPB lights up in red, and we see true printing out in the serial console. Now when I take my finger off button A, look at that. It starts to print false, but what we didn't do is we didn't do anything to change the pixels from red, so they're going to continue to be filled in red as soon as we press the button just once. Well, let's apply what we just learned in a challenge problem. Modify the code so that if button A is pressed, all lights will be red. We've already done that. And if button B is pressed, all lights will be blue. Now this means that you need to set up a button B and write code to detect if button B is being pressed. A properly coded program should work like this. So why don't you pause, give this a shot. When you're done, resume, and let's compare answers. Now coding this up is pretty straightforward. We set up button B the same way we set up button A, so I'm going to copy these two lines that we described as sort of a software Lego. I'm going to paste them below, and I'm just going to change every place that refers to button A to button B. So first I'll change the name of the object that we're creating to button_B. Then the value that I pass into digital in out will be board.button_B, and board.button_B knows exactly where button B is on our board. Then I need to make sure the line below refers to button_B, that object that I just created, and there are no more changes on this line because we're going to do the same exact thing as we did for button A. Make sure that we switch to input, and we set this so that the pull down is set. We actually refer to this as using the internal pull down resistor. But for now, just remember, you want to use those built-in buttons. This is the code that you need. Then we'll code things up the exact same way in our while true loop, so I'm just going to copy the two lines from my if statement for button A, paste them below, make sure the two if values are indented at the same level, and in the value I just pasted, I'll change this so that it reads if button_B.value, and if that's true, I'll change pixels.fill, passing in blue. Now I'm going to delete the print statement up here because that just applies to button A. Feel free to put in a button B print statement if you want to see how that value changes. But I'm going to go up here and open the serial monitor. Now false continues to show here because that was our old code. That's still executing on our board because we didn't stop it with a Control-C. Press save. The new code takes over. Nothing's printing to the serial console. Let's press A. It's in red. Press B. Nice. It's blue. Press A. Hold it down through the half-second delay. Red again. B, blue again, A, red again, B, blue again. Nice work. Now in our next step, let's learn how we can show red if button A is pressed and held, blue if B is pressed and held, but if neither button is being pressed, let's turn off all of the lights. Now we currently have two separate if statements. If we press button A, the lights are turned on red and remain red, and if button B is pressed, the lights turn blue and remain blue. Now these are two separate if statements. What we're about to do is combine these two if statements into one statement and introduce a third part. So the code we're about to write will check to see if button A is pressed. If so, it'll turn the lights red. But if button A is not being pressed, then we'll check to see if button B is being pressed. If that's the case, we're going to light the lights up in blue. But if neither button A nor button B is being pressed, then we'll turn all the lights off. And here's how we're going to do this. We create a multi-level if statement using an elif clause that'll check to see if another if condition is true, and at the end we'll add an else clause which will execute only if all the clauses in the statement above it are false. So first we check to see if button A.value is true. That means if button A is currently being pressed, the button is actively being held down. And if this is true, then we perform any statements indented directly below this if statement. So we fill in the pixels in red, and if this is true, after executing any statements indented below it, we skip these other two clauses, including any statements indented under elif or under else, and we get to the bottom, and if there are no extra statements at the same level as the if statement, then we're going to loop back to the top of while true, and we're going to start looking through the if statement again, checking to see if a button is actively being held down or not. Now what if button A is not being held down? Then this first part of the if clause is false. So we skip over any statements that are indented directly under it, and then we check to see if this next part is true. So in this next clause in the if statement, it starts with elif for else if. So we can read the statement like this. If this first part is true, then execute any lines indented below it. Else if this statement is true, then execute any indented lines below it. Now, if the else statement is true, button B is actively being held down, so we're going to execute all statements indented below it, and there's only one statement here that's going to turn the lights blue. Then when we're done executing this statement, we're going to jump past the else statement and any statements indented underneath else, and we're going to end up looping back to the start of while true, and we'll examine our if conditions again. Now you can probably guess what happens with this last clause, the else clause, if we have a situation where it's false that button A is being pressed, and it's false that button B is being pressed, then all of the conditions under both of those clauses are skipped, and then we execute any statements that are indented after else. We'll shut off all the lights with the statement pixels.fill, passing in black. Then once we do that, we loop back to the start of while true, reevaluating all of the if conditions in this statement. So let's code this up and see how it works. So I'll close the serial console, and then I'll change the second if statement, making it part of the original if statement by adding el in front of if. So you can read this: if button A dot value is true, turn the pixels red, else if button B value is true, turn the pixels blue. So these are two clauses in the same if statement. Then below the statement indented after the else statement, I'm going to outdent, and I'm going to type an else clause here. Make sure that you add the colon, and indent it underneath that. If neither button A nor button B is being pressed, then I'll execute what's after else, which is pixels.fill, and in parentheses I'll pass in black. That's going to shut off all the lights. I don't need to delay anything with time.sleep, so I'm going to delete this statement. Then I'll head up and open the serial console just to make sure I don't have any errors. I'll click on save, no errors. A red, off none. B blue, off none, A red, B blue, A red, B blue, off none. Now if I press both buttons at the same time, red lights up. Even if I press and hold down blue at the same time. If I hold down blue and then press red, red lights up as well. Why is that? Well, our code executes from top to bottom. If we evaluate if A is being pressed first, then if A is being pressed, we turn the lights red and we skip over everything else in our if statement. So we never look at the statement checking to see if button B is being pressed, and so that's why the A press will always take precedence over the B press. Now this leads us to another interesting question. If we want to test to see if more than one thing is true at the same time, let's say if button A is being pressed and button B is being pressed, and if both of those things are true, let's say we want to light the lights up in green, well, we can do that with a compound conditional statement using the AND statement, and here's how. All we need to do is put AND in between two things that we'll evaluate as true or false, meaning between two Boolean values or expressions. And if the left side of the and the right side of the and are both true, then the entire statement is considered to be true. And if the entire statement is considered to be true, then we can execute any statements that are indented below it. But if one or both of these values is false, then we skip on and we evaluate any other clause that's part of the if statement. This seems super handy. Let's try it out. Now back in Moo, I'm going to put lel in front of the first if statement because that's no longer going to be my first if statement. And then just above this, I'm going to add an if statement that says if button underscore A dot value and button underscore B dot value colon. So if both these values are true, then I'll press return. Anything indented underneath this will execute, and I'm going to enter pixels dot fill, and inside parens I'll pass in green. Now if either button A isn't pressed, button B isn't pressed, or both aren't pressed, then I'll go ahead and evaluate the elif statements or execute the else statement. So let's see how this works. I'll open the serial console, click on save, no errors, our moment of truth. A red, B blue, A red, B blue, both green, woohoo! But if we take off B, we turn red. If we take off A, we turn blue. Again, press them both, they turn green. Mission accomplished. Nice work and statement. Now just remember, execution order matters. So if I go back in here and I take my first if statement and then turn this into an elif statement, then highlight and cut these two lines out, then turn button underscore value into an if statement, so it's the first statement in the clause, paste my compound conditional just before the else statement, then this is bad code. Because if I go ahead and execute my code, I'll see that if I hold down button A or button B, those statements are true, and I'm never going to reach the condition where I can evaluate if button A and button B are both being held down. I'll never see green lights. Now let's finish up by taking a look at the truth table for the AND statement. So for the AND statement to be true, we have to have a true expression on both the left side and the right side of the AND statement. If either the left side is false or the right side is false, or both of them is false, then the entire statement is considered to be false. So an AND clause is only true if both sides are true. This side and this side. Now there's a related statement called the OR statement. And the OR statement returns true if both sides are true, or if either one side or the other side is true. So the only time an OR clause is false is if both sides are false. So we haven't seen OR yet. You can certainly experiment with that in your code, but know about it because you will see it in your career as a CircuitPython programmer. And an OR are both important tools for working with compound conditionals and Boolean logic. So Python programmer, once again, we had a lesson full of big learning. We learned how to use the digital I/O library, set up buttons, recognize button presses, work with conditionals, if, and the else statement. We worked with compound conditionals, including and or. We showed the importance of execution order in our code, and introduced truth tables for Boolean logic. Hope you're feeling good about those skills, coder. Keep at it.